In this video, I'd like to explore adding infinitely many numbers together. And of course, bring in our old friend similarity from geometry. But we'll start with Zeno's paradox. And Zeno of Elea was an ancient Greek who belonged to a movement called Cynics, which, contrary to the name, was actually quite a cool philosophical movement, sort of similar to Stoics, but more trouble. So Zeno in particular questioned all sorts of things, even something as basic as movement. And in this particular paradox, he argued that Achilles, who was a mythological figure, super strong, super fast, could never win in a race against a tortoise, as long as a tortoise had a head start. So how on earth could he argue something like that? Well, first, let's actually bring a little illustration of Zeno's idea. And this illustration belongs to Martin Grandjean, and I found it on Wikimedia. So thank you very much for that. So this is the illustration, and you can see the point on the left with a cool little ancient helmet above it represents Achilles' starting point. And the point on the right here up the top is the tortoise, where the tortoise starts. Let's say there's 100 meters between them. Maybe not. Doesn't matter. Okay, so the tortoise has a head start of 100 meters. Now, Zeno reasoned as follows. Zeno reasoned that, okay, Achilles is a lot faster than a tortoise, but he still needs some time to reach the tortoise's starting point. In that time, the tortoise will be able to make some headway. So let's say after some time A, Achilles manages to run this 100 meters, and Zeno assumed Achilles was 3 times faster than the tortoise. I think he was probably being a bit unkind to Achilles, but let's say that's true, that in that time A, that Achilles runs 100 meters, a tortoise will run 3 times less, so a distance 3 times shorter. So this distance will be 100 over 3 meters. That's what the tortoise has covered in that time. Okay, fine. Now Achilles wants to keep on running. So Zeno basically reasoned now in the second step, so he's decomposing the race into these steps. Achilles needs to reach the tortoise's second point. Okay, so he's run this 100 meters. Now he's got to run 100 over 3 meters. This 100 over 3 meters. And that, of course, will take him a third of the previous time. Because the distance is a third of the previous distance, the time will be a third of the previous time, right? But he still needs to keep on running. And in that time, the tortoise will cover a third of the distance that Achilles had run. So 100 over 3 and over 3 again. So 100 over 9. And so Zeno reasoned that the Achilles will always play catch up to the tortoise. So he's decomposing this race into these steps. First, Achilles has to reach the tortoise's starting point. Then the next point after that, but the tortoise has already moved on a bit. And then he keeps on playing catch up to the tortoise each time the tortoise moves on a bit more. And so even though the distance between them will keep on shrinking, the actual number of steps required for Achilles to reach a tortoise is infinite. He never actually quite gets there. He needs to always cover the distance up to the tortoise's previous point, in which time the tortoise has moved on. And so that's an impossibility, as Zeno reasoned. Okay, there's actually various aspects to this paradox, but mathematicians grapple with a very specific aspect of it, and that is the time needed to do that. So even though Zeno is decomposing, is breaking down the distance into these infinitely many bits, the sum of those bits is not necessarily going to be infinite. Well, let's actually think of it as follows. Let's even think of the time. So the time that Achilles spends running. So Achilles' time. Let's do Achilles' time till he catches up. Equals, well, first it's the time needed to catch up to the initial tortoise position of the tortoise, A. Then the time needed to reach tortoise's second position, A over 3, plus the time needed to reach tortoise's following position, and so on. And so we see that it is actually the way Zeno reasoned. There's infinitely many shrinking bits of time. So what does that actually mean, right? It means that the very first thing that might occur to you is each term contains an A. We could take this A out. It's a common factor. So what's left is 1 plus a third plus a ninth, which is 1 over 3 squared, plus 1/27th, which is 1 over 3 cubed, and so on. Okay? And how can we now represent it so we get a little bit of an idea of what this sum could represent? Okay, so let's actually represent graphically what that funny infinite sum stands for. So we're just going to firstly draw a segment of length 1. So just a segment of length 1. And that's our first term, 1 plus, and then the next one was a third. So next we're going to join to it a segment of length a third. Okay, so, and there's your segment or interval of length a third. Okay, so that's the first two terms. And now we'll tack on the next one, which was, if you remember, 1/9. Okay, so that's 1/9. Okay, so graphically we can sort of begin to get a feel for what's going on. And then 1/27th, right? So it's growing. This sum is growing. We can see the length of the segments growing, but they grow less and less and less. Now, since the segments actually are shrinking, the successive things we're adding are going down by a ratio of a third, a constant ratio. It suggests we do something geometric. We draw a figure of some sort. So where perhaps we can apply this property that we're adding things that are shrinking by a constant factor, right? So I suggest, why don't we try to draw a square? Okay, so here I drew a square of length 1. Okay, and so that square corresponds to our first segment. And you might ask yourself, well, how does that help us? Well, let's see. We're just playing at this stage. We're just experimenting. So then for the second segment, right, length a third, we're going to draw a square, again, of length a third. Okay, so that's the next square. And then the next segment is of length a ninth. So again, we're going to join in with a square of side length 1/9. And similarly for the next one, the really small one, 1/27th. And of course, in principle, I should keep going and going and going, but it's not going to look so good on this illustration in GeoGebra. So we just have to imagine that these segments keep on going and the squares keep on going. Okay, let's think what's going to happen as we go down this square. So what do I mean go down the squares? Let's actually put a few more vertices. L is already there. Let me just put a few more vertices. Let's put one in Q. And let's put an R here. And let's think what's actually happening as we descend from vertex L to vertex Q, from Q to R, and then down to the next corner here in D, right? What's actually going to happen? Well, the descent, the slope of this descent is always going to be the same, right? So if we go down from L to Q, for example, right, we go down 2/3, we put in 2/3, right, and you go 1 across, okay? So then the slope is actually negative 2/3 if we descend that. So if we descend, let's actually try to do that. Let's do from L to Q, the slope of the segment H1 is going to be 2/3, right? Because you've gone down 2/3 and you've gone across 1. So that's 2/3 over 1. Now, as you go down from Q to R, what's going to happen to the slope? It's going to go exactly the same way, right? The ratio is going to be 2/3 because all the squares are in proportion. So we can calculate this side is 1/3, this side is 1/9. If you subtract them and divide by 1/3, you're going to get again 2/3. We can join them together and you can see that it continues. This I1 continues from H1, right? Has exactly the same slope. And the same is going to happen if we continue from R to D, and so on. And so if we actually continue joining the segments, or just simply extend this line until it meets the base, it's going to meet the base in the point where our segments 1 plus 1/3 plus 1/9 plus 1/27 and so on, where they actually terminate. By terminate, I mean the infinite sum reaches its limit, which in a way represents where all these numbers, 1 plus 1/3 plus 1/9 plus 1/27 and all these other ones that are always multiples of 1/3 of the previous one, to add up to. Okay, so this is a representation of this infinite sum. Base side of this construction represents the infinite sum of these numbers. Now, how can we actually compute it? What is it going to equal to? Well, hopefully this construction suggests that. So you might want to sort of pause and think about it and see if you can work it out for yourself. That might be useful. So the important thing to notice here is the similarity of two triangles. The triangles AML and triangles LPQ. Right. Those two are similar. Why are they similar? Well, hopefully we can work it out for ourselves, but basically because of parallel lines. Okay, so we can actually check that the angles are going to be the same because of the parallel lines postulate. Right, so those two triangles are similar, and therefore they have the same proportions. Right, so and the proportion that we actually care about here, the proportion is of the big triangle AML is the proportion AM over AL, right? AM is the side we want to find out. And AL is actually just equal to 1 because it's the side of our original big square, right? And so that proportion, if we can find that out, is going to give us our side AM, right? And if we look at it and compare it to the triangle LPQ, right, the corresponding sides are LP and PQ. And LP is again 1. So the proportions we get are AM over AL is equal to the corresponding proportions LP over PQ, right? Now, as I said, a bunch of the sides are known. So AL is 1, as is LP. And PQ is just 2/3, like we've seen before. So we can immediately write down what AM is actually equal to. It's just 3/2, which is 1.5. So in that way, we've actually summed up the times coming back to our original idea about Zeno's paradox. We've added up the times Achilles is needed to catch up to the tortoise's position. It's just 1.5 times the original time A. The time he needs to run 100 meters times 1.5, and in that time he will catch up to the tortoise. Now, this construction actually works perfectly well for other cases of infinite geometric series, not just the ones with 1/3. So I encourage you now to try to check your understanding by writing down different series. So perhaps the terms go down by 1/4, like so 1 plus 1/4 plus 1/16, and so forth, or 2/3. Just as long as they go down by the same factor, right? Write that down and then construct these squares and see if you can add up this series using this construction that I've described. And then that would be an interesting exercise as well. Try to write down the general formula so that rather than 1/3, 1/4, or some other factor, we have a general ratio R. And what is the sum of the infinite geometric series for this general ratio R? Okay, thank you for watching.